All right, so today I wanted to discuss this generalized Caylor-Ricci flow in this non-degenerate case. And so I'm going to kind of, discuss it in any case in a fairly broad way, but which hopefully kind of feels inevitable given everything else that we've discussed up to this point. So first of all, what do I mean by this non-degenerate hypothesis? So I have a generalized Kähler structure like this, and then sigma, as usual, is the Poisson tensor. So 1/2 G inverse bracket IJ. And by non-degenerate, I just mean that sigma is non-degenerate as a pairing. And then I'll define big omega to be sigma inverse. Okay. And of course, the main example, that we have of structures like this, of course, are hyperkähler. So if I have M 4M G I J K, then of course this is non-degenerate generalized Kähler, and this tensor sigma will just be like the inverse, but using the quaternion relation, sigma will be the inverse of the omega k Kähler form. So yeah, sorry, maybe I should at least write the word hyperkähler. Okay, and then of course we've seen from, I guess, from a couple points of view how to deform these structures. So if I have a one parameter family of functions, smooth functions, and then xt is sigma dft, so I can get these Hamiltonian vector fields xt, and then phi t is the one parameter family of diffeomorphisms generated by xt. Then this flow construction in this setting tells us, well, at least the way I think of it is that so big omega I phi t star j is generalized Kähler, where the point is, of course, using the non-degeneracy. If you know omega I and a complex structure, then you can recover the metric just like algebraically from those tensors, and then with the metric recovered sort of according to this formula, then that triple is generalized Kähler. So the point is, like, algebraically these three suffice to recover the metric, and then with that metric, that the triple gi phi t star j is generalized Kähler. And yeah, and then of course, just as an important remark, of course, the time dependent metric is of course not equal to the pullback of the original one. So it's doing something geometrically non-trivial to the metric, even though even though J is just being pulled back by diffeomorphism. Okay. So yeah, so this is I guess arguably the genuinely like new part of generalized scalar geometry is this sort of what's happening on the in this non-degeneracy locus, or more generally in the directions where sigma is non-degenerate. And so in any case, we're just looking purely at the case where it's completely non-degenerate everywhere. And so, you know, what we want to ask is just what's the geometry of this generalized scalar Ricci flow? What might it do, and what might that imply? And I'm going to discuss that. So first of all, what is the Calabi-Yau quantity? Can ask this question. And the point is that, well, there's a different way to think about these generalized scalar structures. So I can define these two symplectic forms, F plus minus, which is G I plus minus J inverse. So it follows from the integrability conditions that these are both symplectic forms. This is the sort of equivalent way to think about these non-degenerate structures. And in fact, these are F plus minus are the pure spinors defining the two generalized complex structures defining the generalized scalar structure in this fashion. Okay. At least, I guess maybe up to a B field equivalence. They're naturally the so both generalized complex structures are of symplectic type using these two symplectic forms. Okay. And so then it's easy to write down what this quantity phi is, right? So this quantity phi we usually define to be the logarithm of the ratio of the Mackay pairing of the two pure spinors defining the generalized complex structure. And in this case, what that works out to is log, so we can think of it in a couple ways, like F plus to the N over F, oh, maybe my N is, okay, yeah, maybe I have my dimension 2N, not 4N. That's, anyways, it's the logarithm of the ratio of the volume forms associated to F plus minus, or even more simply, we can express it purely in terms of the complex structures. It's probably there's some signs I need to get right, but log determinant I minus J over determinant I plus J. In any case, up to some constant factors, this should be right. So this is like the right sort of Calabi-Yau function as defined by Marco. And you know what we saw for like Kähler-Ricci flow and for like generalized Kähler-Ricci flow in the commuting case is that this Calabi-Yau quantity in an appropriate way is kind of like a Ricci potential for the Bismuth-Ricci curvature, and that you can more or less understand generalized Kähler-Ricci flow by flowing the scalar potential for the metric according to this quantity phi. And the point is that that picture holds exactly in the non-degenerate case. That this is the point. So what exactly does that mean? So we have some important curvature identities. So first of all, I can take the difference of the two Lie vector fields. Now, this is precisely the vector field which governs the flow of J, right, along the generalized Caylor-Ricci flow. It's precisely by this vector field. And so, again, the formula, sort of according to the philosophy I just described, the formula for what this ought to be is easy to guess, but not super easy to prove. This is sigma d phi. Okay. So again, if we're expecting this generalized Caylor-Ricci flow to sort of flow by these canonical transformations guided in a natural way by the Calabi-Yau quantity, this is somehow what it had to be. And in fact, it's true. I mean, this has to be computed. And also this quantity phi is a natural sort of, this doesn't really make it look much like a Ricci potential. I mean, this is more like describing the torsion, but in fact, it's also a Ricci potential. So if I compute the I Bismuth-Ricci tensor, then again, this formula, the way that I wrote it in the commuting type case, we realize that it could be like djd of the Ricci potential, and the same thing is true here too. This is djd phi. Well, maybe I have a sign wrong. Yeah, I think sorry, minus. So again, yeah, so in this non-degenerate setting, we see this this Calabi-Yau quantity precisely determining the two key objects. So we're sort of flowing the I Kähler form by the I Bismuth-Ricci. That's determined by phi. And we're going to end up flowing J by this difference of Lie forms, which itself is determined by phi. Okay. And yeah, and then that's the result. So the proposition which can be proved. So if you have, let me just make the dimension 2. So if this is a generalized Kähler, non-degenerate, and GT I JT is the generalized Kähler-Ricci flow with this initial data. Then, in fact, this JT is just phi t star J of the initial J. Where phi t are the Hamiltonian diffeos generated by the time-dependent Ricci potential phi t. Okay.
Jeff?
Yeah.
The formula of the Bismuth-Ricci, is it symmetric in I and J, maybe up to sign, or I mean, if I exchange I and J is true?
Where I have to think about it. Maybe with a sign. No, I think it should just be true on the nose. Yeah, I think without a sign even. Maybe I need to think about that. It's definitely true, perhaps up to a sign. Yeah. because there is, yeah, obviously J plays some like distinguished role. It's in this, in the way I set things up. But in any case, yeah, it's essentially true, I think, up to a sign maybe. So yeah, so the point is that well, yeah, so this is just what I was saying. So we exactly recover this flow sort of as a canonical instance of this flow construction, where the function sort of guiding the flow is exactly this Calabi-Yau ratio. Okay. And just like a general question that I have, that sort of nags at me that I still think is interesting. I mean, I don't know, it might be a little bit misguided, but so, I mean, as discussed by Francis, this then describes a one parameter family of Lagrangian submanifolds of, say, M cross M, endowed with a particular symplectic structure. And I guess the question I have is generalized Kähler-Ricci flow, or maybe the right way to ask it is, can this interpretation as a flow of submanifolds yield some new analytic estimates? I don't really have a very precise question, but it's sort of surprising to me that somehow this sort of purely intrinsic Ricci flow equation naturally is producing some flow of Lagrangian submanifolds, where sort of the special Lagrangian condition is what's being aimed for. And I mean, this like Lagrangian mean curvature flow in Calabi-Yau space has all this kind of special structure to it. And it's very, well, it's sort of loosely analogous to that picture where this function phi is like the angle function somehow. But I guess it's not clear. Maybe a bit more of a precise question is, like, is the second fundamental form of these Lagrangian submanifolds? Well, I mean, I guess the problem is you don't even really have a metric on this space. So I don't know, is there a natural metric to put on this space such that the second fundamental form of this submanifold has some natural relationship to the flow, I guess, is maybe the question. But in any case, I guess it's a very intriguing point of view but for which I don't yet see a way to buy something analytic from it, but it seems like it should be possible. Okay, so yeah, and then I guess as a further remark.
Can you read again what is the statement of the proposition? Is that if you have a solution of generalized Kähler-Ricci flow where I is fixed, then JT has to be of this form? Is it the statement?
Yeah. I'm studying it like in this I fixed gauge as usual. Yeah.
And this
so
implies that
all it's moving
JT
is G and J. I mean, yeah. So actually, a further remark, of course, is that I mean, G has a PDE which guides it, but actually you notice, right, that like this encodes everything, right? So as we remarked above, this flow construction only requires you to move J in this setting. And once you know J and I and omega stays fixed, big omega stays fixed, right? You recover the entire structure. So in a sense, this is the entire flow equation now. This is the entire generalized Kähler-Ricci flow now.
And in your question, the symplectic structure on M cross M is omega minus omega.
Yeah, I think that's right? Francis, right? This is like endowed with big omega direct sum minus big omega.
But for different complex structures, I think. One of them for I and one of them for J.
You mean like I omega and J omega? Or
Oh, yeah, no, that is the right one, just for the real symplectic manifold.
oh, okay, yeah.
But so it also has the holomorphic structure.
Mm-hmm. Okay, so yeah, so a remark that comes out of this discussion as well, I guess, yeah, I guess is sort of comes out of item 2. Due to item 2, this formula for the Bismuth-Ricci, and the fact that because we have in this setting like a global holomorphic symplectic forms, in fact, the first Chern class of the I complex manifold is 0 even in bot Chern. So this rigidity result of Godeshan that I mentioned before tells us that if this is compact and the phi is constant, so if I can actually solve this Calabi-Yau equation, then in fact, let me just say, in fact, it's hyperkähler. Okay. So we discussed at some point that if you have like Bismuth-Ricci flat and the first Chern class is 0 in bot Chern sense, then it has to be Kähler. And then in this case, because you have a holomorphic symplectic form, it ends up being hyperkähler. Okay.
You said that you need phi to be constant for this?
Oh, certainly. Yeah, yeah. I mean, just like the local deformation construction takes hyperkähler to something genuinely generalized Kähler, genuinely non-hyperkähler. Yeah, I mean, we certainly need like a PDE to get the rigidity, to get something like this.
How does this follow from the rigidity of Godeshan?
So basically, this general result that we had mentioned is he shows if you have say the integral of the Chern scalar curvature against a background Godeshan metric is bigger or equal to 0, but C1 MI is 0 in bot Chern sense, then in fact this scalar curvature is identically 0. And so there's some further curvature identities. So the point is this is Chern scalar curvature, and the point is that this Bismuth-Ricci flat equation tells you that so rho bismuth I vanishing gives you this identity for the Chern curvatures, where here I mean this to be a big S minus a certain torsion squared. So this is the this is what's called like the second Chern-Ricci. Then this is 0. And so in particular, actually, I guess I don't even need this equation. This is an equivalence, but in particular, in any case, it implies that the scalar curvature minus the magnitude of the torsion squared is 0. So basically, if S has to vanish, then the torsion has to vanish, right? And so once the torsion vanishes, it's scalar, and then it's Ricci flats, and so and it's hyperkähler. Does that answer it? Okay, so sorry.
You're just using the rigidity to get from generalized scalar to Kähler.
Well, yeah, but then it's still so now it's Kähler, and so like for instance, the Bismuth connection is just the Levi-Civita connection now, right? And so it's still Bismuth Ricci flat, and so now it's just Kähler and Ricci flat, and so it's Calabi-Yau, and then we have a holomorphic symplectic form, so then it's hyperkähler.
Right.
Yeah. Okay. So yeah, so so what might we expect then for the so there's sort of then a, based on our sort of general discussion of how these flows should go, there's a conjectural existence and convergence. So given M2N G I J and generalized Kähler, non-degenerate, the solution GT I JT to generalized Kähler-Ricci flow, this initial data exists on an infinite time interval and converges to G infinity I J infinity which satisfies phi constant and is thus hyperkähler as discussed above. Okay. So, I mean, at least from this sort of PDE point of view, there's kind of no reason this shouldn't be true. But we note if this is true, then it has a really strong consequence, right? So if true, then all non-degenerate GK are just flow deformations of hyperkähler. Okay. So in other words, this example we gave at the start would then be the only way to construct them. And I do think this probably is true.
Well, do you believe it's true without assuming that hyperkähler metric exists?
Yeah, I do. I don't know. I just
want to point out that will be probably the first result that shows some sort of a priori non-Kähler condition implies Kählerness. You know, there is this conjecture of Jan Streets that if you have a tamed pluriclose
like Hermitian
structure,
symplectic.
yeah, then should be Kähler, but nobody can prove this. This will be probably one instance that can be true.
That's true. Yeah, that's true. Okay, so I want to state now, so this I think is the natural conjecture for this setting. And now I want to state a theorem showing what we can prove. And this is joint with Vesti. So suppose we're given M2N G I J non-degenerate generalized scalar, and assume, this is a big assumption, but we assume that already this is a Kähler manifold. I'm not assuming anything about the metric G, just that as a complex manifold, it admits Kähler metrics. I just needed to admit some Kähler metric. Okay. Then the solution to generalized Kähler-Ricci flow with the given initial data does indeed exist for all time. And in a kind of weak sense, can show, for instance, that phi minus lambda in some L2 sense with respect to a background metric goes to 0. So there's various kind of strengthenings of the weak convergence that we can prove. Here I just state the simplest one, which at least gives the idea. So so what have we done? So we at least proved the existence part in the case that your manifold admits some kind of Kähler background, which again purportedly maybe is the only realistic case anyways, but of course it would be better to not assume this, to not assume this. But we need it for some technical reasons to get some estimates. So we prove the global existence, and then we prove, at least in a weak sense, so whatever this constant lambda is, this is topologically determined what it could possibly be. And then phi approaches that topological value, at least in a weak sense. So this, for instance, shows that if it does, if it's at least sort of controlled at infinity, in the sense that you can take some kind of subsequential limit, then that limit will be hyperkähler. And I want to say a few ideas in the proof. At least the sort of most conceptual part of the proof I want to describe, because again, it sort of ought to be easy to guess based on hopefully the way I presented, Tsau's theorem and then this commuting case. So one of the main things we can hope for, I mean, if this is going to be true, and if the analogy with Kähler-Ricci flow is supposed to hold, then remember, we always call this heat operator to be the time dependent. H is the time dependent heat operator. And so that one of the key geometric facts was to apply the heat operator to the Ricci potential itself. And in all these cases we saw before, it's 0, and in fact it's 0 again here. So this is a crucial point. So this Ricci potential on the nose just satisfies the time-dependent heat equation. And this part actually is completely general. This doesn't require the Kähler background. This is totally general. And then so again, immediately what you get from this is a further estimate. So this is first. And then you can also then apply the heat operator to the gradient of phi, measured with respect to the time varying metric as usual. And for our purposes, maybe it's good enough to just say it's less than or equal to negative norm Hessian phi squared. And so in particular, this will be like less or equal to negative rho bismuth I squared. So we have this identity showing that phi is this potential for the Bismuth-Ricci. And so indeed, this positive function is a subsolution to the heat equation, and it even has this favorable negative term on the right-hand side. And again, as I said, in the commuting case, this is sort of loosely analogous and plays a similar role analytically to the scalar curvature monotonicity for Ricci flow. Okay. So in particular, we get a sort of a heat, we apply a heat operator to some natural quantity, and it has a sign, in this case, a very useful sign, because this is a positive quantity and then it has to be decreasing. So it's sort of pushing towards just being zero. And moreover, it bounds the time derivative of the metric squared. So these two things strongly point towards the conjecture holding, but then in the end, we really do have to try to emulate these maximum principle arguments, sort of genuinely getting upper and lower bounds for the metric tensor along the flow. And then here is where the, and so this part I just want to skip completely. So with the Kähler background hypothesis, the point is you can use 1 and 2 to estimate this alpha reduction of the background pluriclosed flow. And here, I mean, again, this sort of, it still seems like there's room to better exploit the sort of local potential theory for generalized Kähler metrics, because you see, for instance, at this stage of the proof, it actually doesn't even really, I'm not even really using the generalized Kähler structure. I mean, I guess I am, because I'm using these nice evolution equations to help in the analysis, but more or less, I'm using the fact that I can describe the time-dependent pluriclosed metric using a 1-0 form. So clearly something is being lost in this analysis. But in any case, yeah, it would be, I guess, interesting if the sort of potential theory could be brought to bear to make this tighter, I guess. But yeah, so I guess this is a, yeah, I mean, this part is quite technical, and more to the point, all of these estimates degenerate at time infinity. So these two, of course, give estimates which are uniform all the way out to time infinity. But the actual estimates, upper and lower bounds for the metric tensor, all go away as time goes to infinity. Okay. And okay, and then maybe I'll just say one more thing. So we have a kind of moment map functional, which is monotone along the flow. And this is what gives the weak convergence. Okay.
Can you say how that works, please?
So yeah, I don't know, Vesti, can you say how it works? Well, it's sort of it's akin to this moment map picture for the Calabi-Yau equation that Joel Fine found. So let me see. Let me remind myself.
Yeah, it's maybe to say just that it's this functional is just a natural Kempness functional in this formal GIT picture, and it's it's essentially the norm of the momentum map with respect to.
I don't know, is that okay?
Yeah, that's okay.
Yeah, it is. I think, yeah. So it's like I said, this was done in the sort of Kähler setting by Joel Fine. He defined this, but I think in that case it was a little bit maybe overlooked because we already kind of knew all the analysis and estimates for Calabi-Yau Kähler Ricci flow, anyways. But in our case, it was useful because, well, in any case, it was the best that could be done.
So to be precise, I think Joel Fine considers the prescribing volume form in the classical Calabi.
Oh, that's right.
Calabi setting, whereas in our case it's a little bit more involved, but it's reminiscent to that. It's not the usual GIT picture in the Kähler setting where the scour curvature is the momentum map. It's more of this volume prescribing setting that we found.
Yeah.
The GIT interpretation.
Well, and actually, I guess as we sort of more recently discovered, although this isn't in the paper, there's even a kind of a different moment map kind of point of view where we can use this like generalized scalar curvature to define something like Mabuchi energy. And this is also monotone along the flow and can also give some kind of weak notion of convergence.
Yeah, and this may be more natural actually, just to look at the results. So we have now a generalization of Mabuchi function also. So it will be proper and by standard argument, you have this L2 convergence.
Okay, so yeah, so
okay.
in any case,
where is this generalization of the Mabuchi function? Is it already on the archive or
no,
okay.
No, but it's relatively easy to guess, I guess. I don't know why we didn't maybe guess it before or try, but I mean, you integrate the generalized scalar curvature against the deformation.
Basically a logarithm of phi. So the integral of logarithm of phi of this case will be quite simple.
Okay, so I guess this was all the results I wanted to discuss, and I just wanted to take a little bit of time to discuss kind of what the general conjecture should be. So what should the generalized Kähler Calabi conjecture be? And I think based on these pictures that we have in the different settings, in the commuting case, in this non-degenerate case, and the way everything has tended to work out, there should be a very simple and clean setup here. But first of all, I think there's kind of two conjectures. So first, I'll say the easy version, which is probably still quite hard. So suppose I have M2N G I J generalized Kähler, and suppose J1 J2 are determined by global pure spinors, psi1 and psi2. Well, maybe I don't want those. Mukai pairing. So then, we have this Calabi-Yau quantity, which I'll still call phi. Okay. And well, what I can basically by a very grinding and maybe not conceptual proof, basically combining the two cases of the commuting case and the non-degenerate case, and also arguing that you have some generic like local structure to these pure spinners, you can recover these basic identities that I said in the we've said in both cases now. So for instance, the difference of the Lie forms should be sigma d phi, and the I Bismuth Ricci form should be minus dj d phi. Okay. So like I said, we discussed proving these in the two cases of commuting and non-degenerate, and you can kind of put together these local computations, at least to prove that these hold where the type change of sigma, where the type of sigma is locally constant. And then you can maybe argue by density that it extends everywhere. But so there's a lot of like conjectures here. So is there kind of a natural proof or something a bit more conceptual, other than just putting together these other cases in a more grinding way?
This part is still a conjecture?
Well, like I said, I have a proof, but it's kind of it's only by sort of brutally combining the two cases we discussed above. It's would be better to, well, I mean, I don't know, maybe there isn't a better one, but I would imagine there's somehow a cleaner way to obtain this.
I see, but it is definitely true.
Yeah. And well, and then yeah, and then so this of course then in turn at least gives us well a description of the generalized Kähler Ricci flow as driven by this Ricci potential phi. Okay. Another basic point, which is not, at least to my eyes, and let me just say, label this A, not to my eyes completely settled, but does the existence of psi1, psi2 imply that this first Chern class is zero in Bott-Chern sense? Okay. And again, this is not really immediately obvious even from this formula, because you need it to be like did of something to be zero in Bott-Chern sense. But of course, we know it's true in all these cases of interest, because you can basically, I mean, basically what you want to do is just to construct a global holomorphic volume form. And the point is, in all these different cases, you of course have that. The commuting case, the non-degenerate case. And in particular, so what's the point is that, yeah, so like this one implies that the flow is driven by phi, sort of in this natural way, unifying all the different cases. And here, if this is true, by this argument that I've referred to a couple times, you obtain that the only smooth limits are Kähler, Calabi-Yau.
I'm sorry, Jeff, I have a question, but doesn't your consideration also include the commuting structure on the Hopf surface?
No, that's going to go under the hard version I want to mention next.
Yeah, but
Because you
which
do not
assumption?
have, you don't have these at the start, right?
So you assume that these are closed pure spinors. Right?
Oh, yeah, yeah,
Okay.
yeah.
Thank you.
And I guess maybe more importantly, it's global. And so, well, if this is true, what it suggests, this suggests that generalized Cayley-Ricci flow with this initial data exists globally, and you can even optimistically say converges to Kähler-Calabi-Yau. Oh, and yeah, sorry, maybe I wanted to say one more thing. So this can be D. And C is maybe to find a moment map or Mabuchi energy, which is monotone, with phi equals constant as critical points. Okay. This actually is not really necessary because we always have this Perelman functional, and this Perelman functional would already tell us, given like A and B, that the only smooth limits are Kähler-Ricci flat. That already follows from this Perelman functional, but in any case, it would be nice conceptually to just have like a more classic kind of energy functional, which yields this behavior as well, and it also could easily help in the actual analysis as well if we had such a thing.
Sorry, I understood that you said you already have this Mabuchi energy.
No, sorry. What I meant was like one nice consequence of C. If you could find such a functional, then it would immediately tell you that all the smooth limits have to just be Kähler, right? That like the only possible limit is just phi equals constant, which is then Kähler, right? And then Kähler-Ricci flat Calabi-Yau. But what I'm saying is that consequence, we already know. We already actually know that because of this Perelman monotonicity, the only possible smooth limit for the flow in this setting at infinity, again, assuming C1 is 0 in Bach-Chern sense, would be Kähler-Calabi-Yau. But C would be a different way to obtain this consequence, and could conceivably help in the analysis as well. But I think this suggests a nice picture, which is that so the generalized Kähler-Ricci flow should exist globally and converge to Kähler-Calabi-Yau. In particular, I mean, this would imply that the only GK structures determined by global closed pure spinners, in fact, are just deformations of Kähler, which I think would be a surprising consequence. And then, I guess like within this, what I think is at least definitely achievable, well, how should this work? Or how might this go? Well, at the very least, assuming Kähler background, well, actually, I'm saying this a little bit out of order. So we would expect this same behavior that we've seen in all the cases so far, that the heat operator applied to this Ricci potential is just 0. Sorry, let me erase this because this should not be required for this. This should just be true, because again, it's true in every case that we know, and more or less the general case is sort of has a product structure involving the 2 cases we already discussed. And then this would also immediately give, assuming this one was true, it immediately gives this inequality of this form. And then now,
You mean heat operator applied to the gradient of phi, right?
oh, yeah. Thank you. And now assuming a Kähler background, there's really, I mean, like I said, this proof with Vesti, it's not yet exploiting any, this stage of the proof is not really exploiting the special structure of non-degenerate GK in any way other than to just exploit these differential inequalities. So essentially the proof would just go through to show global existence. And again, a weak convergence. So, I mean, I think this much is definitely attainable, assuming that these, I think, very, very highly plausible conjectures hold. Yeah, I think it's a very nice picture that comes out of this. And again, I just want to sort of mention, like, the, you know, Calabi-Yau theorem was originally proved using elliptic PDE, and then this proof of Tsao came much later using parabolic PDEs, using Kähler-Ricci flow. But here there isn't really a way to set it up naturally as an elliptic problem. I mean, you could sort of ask the same questions. You could talk about this deformation class this sort of governed by this flow construction, and you could ask, can I find you know, like a Calabi-Yau structure where this phi is constant in every deformation class? And that's certainly a natural question, and it may be possible to set it up as an elliptic PDE, but the generalized Kähler-Ricci flow is just a really natural way to approach that. I mean, it sort of naturally respects this deformation class in the first place, and because the sort of because of this issue I always mentioned, that you don't really have a global description of the time t data along these Hamiltonian flows in terms of just one function. It's not clear how natural that elliptic approach really is, I guess, whereas the parabolic approach is very natural. Yeah, and I don't know, I guess we have most of the crowd here. I had some kind of vague hope as part of doing this learning seminar to maybe try to set up a large collaboration to maybe answer some of these questions in a concrete way. I don't know if anyone is interested in kind of turning this learning seminar into something like that. But for instance, I mean, the people that are more familiar with generalized geometry, I'm sure could give very nice answers to a very simple proof of this, probably could answer this question B, I'm sure. And we could sort of grind these things out in some fashion. I don't know, it was just an idea that I had for this learning seminar. I don't know if people are interested or not. But it might be a fun thing to try in this internet Zoom age or something, if I don't know. But I guess so we can talk about that later. But if that's the easy version, then yeah, so what do I mean by the hard version? So more generally, we notice, for instance, that even this like round Hopf metric, this standard metric S3 on S3 cross S1, which is bismuth flat, cannot be a part of this story, right? And in fact, the two generalized complex structures, which are associated to that to this generalized Kähler structure, are not defined by global pure spinors. So they're just not part of that story. But on the other hand, it's Bismuth-Ricci flat. So of course, it's natural to try to include that in any sort of Calabi-Yau type story. So somehow this case of global pure spinors, I think it's very interesting. But I think that this flow sort of suggests that they're all, well, that they're all deformations of Kähler. Whereas we immediately have, like on the case of the Hopf surface, a case of great interest, which.
Could I ask a question about the thing you just said? So when you say that it suggests that in the case where you have global pure spinors, that it converges to Kähler Calabi-Yau. What do you mean by that exactly? Do you mean that both of the complex structures
will be Kähler?
And Calabi-Yau.
Yeah.
So, but that would imply that the Calabi-Yau metric admits two potentially different complex structures, or are you saying that the complex structures will be the same?
Yes. No, they don't have to be the same. And I mean, just like hyperkähler, for instance, they could be. But I mean, you could have, for instance, just like a product of a hyperkähler structure with, just like a standard Ricci flat non-hyperkähler higher dimensional space or something like that.
Yeah, but then the complex structures, they would be covariant constant with respect to the Levi-Civita, right?
Yeah.
And so that means both of them would be covariant constant with respect to Levi-Civita, and their commutator would be as well. So the Poisson structures would be covariant constant. I mean, there would be there would probably be like a product structure.
Yeah.
So you're saying that it would go to the commuting case.
Yeah.
Yeah, it should be by non-Turing, by Bouville, Bogomolov. It should be product of hyperkähler and Calabi-Yaus, and so the Poisson structure will be non-trivial in the hyperkähler bit.
Yeah.
It's either commuting or hyperkähler.
That's right. Yeah.
That should be the structure. Yeah.
But I mean, and also, I mean, the fact that the Hopf surface, doesn't have closed pure spinors. I mean, you could take a line bundle, the total space of I'm like a broken record. You could take the total space of a line bundle, make a non-compact generalized Kähler structure out of it that does have pure spinors.
Sure. Yeah.
But then you're forced to work on a non-compact space, so you'd have to use a different analytic setup, I guess.
Yeah.
This should be strictly for compact spaces, I think, this structure theorem.
Yeah. Definitely.
Okay.
So let me just make a few remarks about this. What I see as the hard version. I mean, naively, what you might ask is you have like M2N G I J, and maybe all you want to assume is just that this is zero, not in Bach-Chern sense, just that it's zero. And then, well, what can you possibly expect? And maybe it's more, what can you not expect? Kähler rigidity, no way. The Hopf is already an example. Okay, so we have, in fact, it's like Bismuth-Ricci flat. Okay, Hopf has this rho bismuth equals 0, but in any case, it's not Kähler. Can you even expect existence of this in the natural deformation class, or perhaps a flow converges? can we expect this flow to naturally converge to something bismuth flat? And the answer to this is also no. And this is illustrated already by these non-diagonal hop. And so this comes out sort of implicitly because there's this rigidity result, which I believe we mentioned of Godeshan-Ivanov. So maybe I just mention it here. So Godeshan-Ivanov shows that in 4 dimensions, if you have even just pluriclosed, so forget generalized scalar. If you have pluriclosed and Bismuth-Ricci flat, then you have 2 possibilities. You're either Calabi-Yau or you're a round hop. And in particular, your complex manifold has these 2 parameters, alpha, beta. And so what I mean, I guess, by round here is that these 2 moduli are the same. Okay. So we realize these hop surfaces as quotients. So I'm writing everything like out of order. So C2 minus the origin modulo Z1, Z2 goes to alpha Z1, beta Z2. So let me sort of box this off. So they proved this result a long time ago. They don't really quite state it exactly like this, but this is basically what they proved. And so in particular, right, the only non-Kähler complex manifold which admits a Bismuth-Ricci flat structure is a very special hop surface. So this was basically how I guessed. So I knew this theorem and I said, well, okay, so what about these other hop surfaces? What does the Ricci flow do? And you say, well, again, you just make some optimistic conjecture. You say probably it should converge. And then what this Perelman functional tells you is that if it converges, it will converge to a soliton. Okay. And that's in fact what's true. Well, so we know we can't have Bismuth-Ricci flats, but there do exist solitons on these hop surfaces where magnitude alpha is not equal to magnitude beta. Okay. And in a certain symmetry class, these are global attractors for the flow. So they really are sort of, well, they really are sort of optimal metrics from this point of view. Okay, but then we can ask, well, all right, so should we have existence of solitons? Is that the right conjecture? And we can't prove it, but the answer is almost certainly no. The examples should be these so-called type 0 hop surfaces. And so what I wrote here are what's called, this is like called type 1 hop surface. This is some terminology coming from what's called like the Kähler rank. It doesn't really matter, I guess, for our purposes. It's just where that number comes from. But the point is there's a dichotomy between these hop surfaces, and then there's a more general Z action you can put on the universal cover, which is not sort of diagonal in this way. And yeah, so like I said, we cannot prove that they don't admit solitons, at least not yet, but I strongly believe this to be true. And sort of the reason is kind of because this should be, and again, this should be related to generations of complex structure. In other words, it should be a story like related to the story of K stability of Fano manifolds. So again, this is definitely highly conjectural. What I think is probably provable is that these type 0 hop do not even admit solitons. What I mean by this is that you can set up what's usually the standard picture of complex structure degeneration for hop surfaces, where you can have a one complex parameter family of complex manifolds where the central fiber is a type 1 hop surface and every other fiber is a certain they're all biholomorphic to the same type 0 hop surface. So this is the standard kind of picture in the case of like Fano, Kähler, Einstein, where the rough idea is always like, if you try to solve your PDE on the type 0 manifold, you end up sort of actually solving it on the associated type 1. You end up solving it on the central fiber, I guess is the point. Yeah, this is definitely highly speculative, but it's hard not to have this guess after sort of seeing the behavior of these examples. It really sort of, there should be some obstruction of this kind, which rules out the existence even of solitons. But like I said, you cannot rigorously prove this. But yeah, so in a nutshell, I guess.
When you say solitons, you mean also compatible with one of the two complex structures at least? Or?
Yeah. So yeah, I guess we have not, I guess, talked about it too much. So the PDE is like the I Bismuth Ricci curvature is the Lie derivative of omega I. And this is the same as like the Ricci soliton. I mean, I wrote it in terms of kind of complex data, but this is just exactly the same as this kind of critical point equation for the generalized scalar curvature functional. This kind of Ricci minus h squared is Hessian f, and then d star h is I grad fh.
X needs not to be the dual of the Lie form.
Yeah, sorry, yeah, this is important. Yeah, here x is the Lie form. Again, the signs, I don't know, minus grad f.
Sorry, what is this equation?
Yeah, sorry. This is the soliton equation. And this is equivalent. This is equivalent to just the usual. So we had these like Ricci soliton equations. So it turns out it's equivalent to these. And there's some nice structure. So this is all like from the work I did with Yuri. So X is I holomorphic and IX is killing. You have some nice structure to this.
And what is F?
F is this auxiliary function which shows up and it satisfies a separate PDE. So we define this functional script F, right, which involved G, H, and then an auxiliary parameter F. But then you sort of, well, you take the infimum over certain choices of F to define this quantity mu. That's like an eigenvalue for a certain geometrically defined operator. And then the Euler equation for mu involves whatever function F that is achieving the infimum, basically. And there's several different ways to think about it, I guess. But that's maybe the easiest, is that it's just the function achieving the minimum of the script F functional among all choices of like unit volume F. So yeah, I mean, I think the hope for this like hard version, or in any case, the state of work is at a much more basic stage. I mean, like I think even even proving like general convergence of these particular solitons on the Hopf surface, I think is probably a hard question. Well, and basically because we're missing these really nice geometric estimates that come from having closed pure spinners. But, well, I mean, yeah, maybe there seems like various points of view that have been discussed. Maybe even in Marco's point of view, getting global pure spinners on the universal cover can give some nice inequalities even on the universal cover that somehow pass, somehow can be used analytically. That seems not impossible to me. But yeah, I think these are definitely some interesting questions. And I just wanted to say a little bit about solitons as a lead-in, because Yuri will speak next on the existence of these solitons, and then also this construction, I guess, of this sort of Gibbons-Hawking type construction where we construct these big families of complete solitons. But yeah, okay, that's all I had in mind. So I don't know, are there any other questions? Thanks.
So in the hard version, what do you mean exactly by first in class equals to 0? You mean any cohomology?
Just in like H2.
Okay, in H2, but not in.
Yeah. Yeah, and I think it's kind of wild that really, like, as sort of, I mean, I find the easy version, it's a pretty picture, but it's a little bit disappointing somehow, that maybe they're all just deformations of Kähler. I find that slightly disappointing. But on the other hand, this hard version, from a PDE point of view, seems to have all the difficulty of the Fano-Kähler-Einstein case. I mean, so it's probably fiendishly difficult, almost certainly.
Oh, I have kind of questions. Well, there should be some stability issues in all this picture. And yeah, in the Kähler case, of course, in the Calabi-Yau case, we don't see them. But I wonder if there is no such a thing in the generalized Kähler world.
Yeah, I mean, it's possible. I mean, yeah, that's the question, I guess. Like, is there, well, and I guess here, right? Well, okay, maybe I didn't formulate the question extremely precisely. Here, I'm thinking not even generalized Kähler solitons, but maybe even just pluriclosed solitons. So, okay, yeah, so like the existence of solitons in 4 dimensions, the existence and uniqueness. Well, yeah, so okay, so we already know, I guess because of your work, right, that like these type 0 Hopf do not admit generalized Kähler structures at all, right? And so because of that, of course, they will not admit solitons. I mean, I guess, yeah, so here I was thinking even just like existence of pluriclosed solitons. So just this same PDE, but only with the one complex structure. But yeah, but even in the generalized Kähler case, maybe this kind of degeneration picture still happens. You know, why not? Even this example I described, it would not be generalized Kähler, right? Because the type 0 has no generalized Kähler.
Maybe at this point, just to motivate further the idea of inviting Goto, I think he studies just naively the existence of some generalized Kähler structure with constant generalized Kähler scalar curvature, and observes, for instance, on P2, if these are toric, they exist always. But if you take a Poisson structure, which is not torus invariant, then the problem is abstracted on the level of photomorphism groups even. So we could speculate that actually there are very interesting stability condition which involves both the holomorphic Poisson structure and the underlying complex structures.
I see.
And it will be fantastic to see this with the flow as well.
So what is the definition of a scalar curvature that he uses?
Okay, so there is a momentum map picture. You know, when you have a generalized scalar structure of symplectic type, we can fix the symplectic form F and act with the group of Hamiltonian transformations, exactly as we do in the Keller case.
Okay.
And then the question is whether this action is Hamiltonian. And this was proved by Boulanger in the toric setting, and it was generalized by Goto. I think he needs some assumption that I think the generalized complex structure is generated by spinor or something. But essentially, in a very big generality, this is Hamiltonian action, and there is a function, which is the momentum map, and that's what will be the generalized scalar curvature.